Jai Hind to all. Myself Shiwani. In this lecture, I will discuss the points of stereochemistry, that is stereoisomerism. So first thing is, what is isomerism? So isomerism is the phenomena where the same molecular formula but the arrangement of groups are different. They may be of two types. Number one, structural isomerism, and number two, stereoisomerism. In structural isomerism, the functional groups are arranged in different position, while in stereoisomerism, there is the same molecular formula, same structure, but they are joined to each other in a different spatial arrangement. So they occupy a different position in 3D space. So simply we can say, if the 3D arrangement or spatial arrangement is different, the compound will show stereoisomerism. The mainly stereoisomerism is of two types, optical and geometrical. Third, you may say conformational, but in this I will discuss only optical, and then in next lecture geometrical. So the first thing is, what is optical isomerism and what is the condition? So in optical isomerism, the first requirement is chiral and achiral molecule. Chiral means if it shows a non-superimposable mirror image, the compound will be chiral. For example, if we take a ball and its mirror image is look same, and if we superimpose the original ball with the image, we get the same. So this is achiral. But for chiral, if we take a left hand, so if we check the mirror image of this left hand, it look right hand, but if we put the left hand on right hand, we get the different images. So this is called non-superimposable mirror image. So the chirality is if compound show non-superimposable mirror image, then it will be chiral. For a compound, the condition for chirality is it must be attached with 4 different groups. So suppose this carbon, and if it is attached with 4 different groups like CH3, like OH, like Br, and suppose this is NH2. So in this case, the 4 groups are different, and when we check the mirror image, definitely we will get non-superimposable mirror image. So this compound or this form will be chiral. 2-butanol. So if we check the structure of this 2-butanol, 1, 2, 3, 4, because the butanol, the carbon should be 4, and at number 2 position there must be OH. So the structure is CH3, CHOH, CH2, CH3. So in this, if we check the second number carbon, it is bonded with 4 different groups. So this compound will be called chiral. But if any 2 groups are same, suppose this OH, and this is CH3, and this is CH3, and suppose this is H. So in this case, we check there is 2 methyl group which are same. So this compound will be called achiral. Now for chiral center, the next thing is, what is the stereogenic center and what is the condition to be a stereogenic center? So the first condition is there must be a 4 different group, and the second condition, the carbon should be, or the atom should be sp3 hybridized. If it is not sp3 hybridized, it will not show stereogenic center. For example, in case of ammonia, nitrogen, not ammonia. So nitrogen R1, R2, R3, and there is one lone pair. So in this we see that all 3 groups are different and one is lone pair. So the nitrogen is sp3 hybridized and groups are different. So this nitrogen is stereogenic center and this will be called chiral. Now next is optical activity. So in case of optical activity, the first thing is, so here we can say that what is the condition to be optically active. So in this, the first is there must be a stereogenic center or chiral center. Chiral center means sp3 hybridization and 4 different groups. And the second is there must be absence of any type of symmetry. Absence of any type of symmetry means there are 3 symmetry. The first is plane of symmetry, The second is center of symmetry, and third is axis of symmetry. So if any type of symmetry is present, the compound will not be optically active in this condition. Plane of symmetry. Plane of symmetry means if we cut the compound in two equal halves and we get the same or mirror image, we can say, so this compound has plane of symmetry. For example, CH3, OH, H, OH and CH3. So in this, we imagine a plane like this. So here we see that we get the two same form. So this compound has plane of symmetry. It means this type of structure, this type of condition, it will not be optically active. Now center of symmetry. Center of symmetry means if we imagine a line which passes through a center, and if this center, if we take the both two form and which are mirror images of each other, this compound will show plane of center of symmetry. Now axis of symmetry. Axis of symmetry means on rotation theta degree, and if we check the mirror image in perpendicular direction and we get the same structure, the compound will show alternate axis of symmetry, that is AOS. In any condition, if the compound has any type of symmetry, this will be optically inactive. So this is the condition to be optically active. Now, for example, in this case, here we see that OH are on same plane. So if we imagine a half plane which divide this compound into equal half and which are same, so this compound will be achiral, that is optically inactive. But here the structure is same, but two OH, both are in different plane. So if we imagine a plane, but the two are not same, so this form is called optically active, that is chiral. For this is the 3D representation, and in 3D representation, if we check that this carbon all bonded with all different four group, which is this compound is 2-butanol, so this is optically active. Now, how we show, how we'll nomenclate the optically active compound? So generally it is represented as either dextrorotate levo or R and S. This R and S, these two representation generally we take in 2D form. So the first, if the 3D form is given, so first we convert this in 2D form and then check whether it is R or S. For example, this compound, this is C. So it is bonded with 4 different groups: fluorine, chlorine, bromine, iodine. So in this, dotted line show means that is viewer is C from this side. So solid line shows in front of eye and dotted line show rear to eye, viewer. So in this case, Cl, it will go there, I, and fluorine and chlorine we take in perpendicular line. For example, in this, so in this it is clear that viewer is seen from this side. So in this case, solid line shows in front of viewer, that is from in this side, and OH rear, back, that is OH here, and H and COOH, which are represented as a simple solid line. So it is perpendicular to the plane. So first convert this 3D structure or 3D form into 2D form, and then we check whether it is R and S. R is the rectus. Rectus means clockwise. And S is the sinister, that is anti-clockwise. So first we give the numbering, and the numbering, the number 1, it should be based on atomic number of directly attached atom. And if atomic number is same, then check atomic weight. If both are same, then check next atom. In this case, we see that the functional group order, functional group order, we take the functional group order. Now in this case, there are 4 groups and all 4 are halogen. But if we check the atomic number, the atomic number of bromium is highest, so we will give this bromine number 1. Now, sorry, iodine. Atomic number of iodine is more higher, so we will give highest number, that is 1. Now second to bromine, third to chlorine, and 4 to fluorine. Now check the number 4 should be either above or below the plane. So in this case, number fourth is above the plane. So forget this. And now rotate 1 to 2 directly and 2 to 3. So here the rotation is like this, and which is anti-clockwise. So this structure will be S. Now in this case, if we check the atomic number of directly attached atom, so directly attached atom, here is O, here is carbon, and here is carbon. The atomic number of carbon is 6, but the oxygen is of 8. So the first priority, OH, that is number 1. Now, check the atomic number. Both are same, carbon-carbon. Atomic weight is also same. Now check the next atom. But in this case, it is clear that COOH is a functional group. And in a priority order, it is of highest priority. So number 2, COOH, number 3, CH3, and number 4, H. Now, check number 4 is either above or below the plane. So since it is above the plane, so forget this. And then 1 to 2, 2 to 3. So here we see that the clockwise rotation. So clockwise rotation means this compound will be R. So this is basically Fisher RS representation. For example, 2-chloro-2-methyl butane. Butane means the total number of carbons 4. 2-chloro. So at number 2 position there is a Cl. Methyl at number 2 position there is also CH3. And if we draw the complete structure, so it is look like this. So here we see that there is 2 same group. 2 same group means this compound will be achiral. Achiral means it will not show optically active activity. That is, we can't nomenclate as a R and S. But in this compound, I think we have already discussed this. No. So in this compound, OH number 1, because the atomic number of O is 8, and directly attached here is CH2. There are 2 groups, CH2, CH3 and CH3. It is clear that the carbon will be attached here from this carbon and here from this carbon. So both are carbon, that is atomic number is 6 and atomic weight is 12. Now check another. Now this carbon is attached with 2 hydrogen and 1 methyl, where in this case the carbon is attached with all 3 hydrogen. So the number 2 will be given to this ethyl group, and number 3 this, and number 4 this. Now check number 4 either above or below. So in this case it is below. Below means there is no any type of rotation. So forget this. And then 1 to 2, 2 to 3. So here 1 to 2 to 3, here we see that it is anti-clockwise. So this structure or this arrangement will be S. But if the compound is look like this, suppose here is suppose T, and this is suppose D, and this is suppose OH, and here is NH3. So in this case, T and D, T is the tritium and D is the deuterium. Both are isotope of hydrogen, because hydrogen shows 3 isotopes, hydrogen, deuterium and tritium. Isotope means atomic numbers are same. Atomic number is same means 1H1, 1H2 and 1H3. So in this case, deuterium and tritium both have same atomic number, but the atomic weight is different. But here we see that this carbon is directly attached with oxygen and nitrogen. The atomic number of oxygen and nitrogen is very high, or more than hydrogen. So the number 1 priority give to oxygen, number 2 priority give to nitrogen, and then come with hydrogen. And since the atomic weight of tritium is 3, so number 3 tritium and number 4 deuterium. Now check the number 4 either above or below the plane. So in this case, it is not neither above nor below. So first adjust this. Adjust this means in Fisher projection, 90-degree rotation is not permissible. We take 180-degree rotation. The best easiest method is make any 2 pair, adjacent pair. So suppose we make this pair, and if we interchange the position of 1 pair, it will be a 90-degree rotation. If we interchange the position of both pair, it will be of 180-degree rotation, which is permissible. That is, in this case, 4 and 2. Now 4 and 2 become 2 and 4. 1 and 3, it become 3 and 1. Now number 4 is below the plane, so forget this. And then 1 to 2, 2 to 3. Now the rotation is clockwise, so this will be R. So what is the summary? If the number 4 is either above and below the plane, leave it. But if it is in front of viewer or rear to viewer, then make 2 pair and interchange the position or interchange the number. If you interchange the number of 1 pair, it will be of 90-degree rotation, which is not permissible. So generally 2 pair and interchange this position, so it will be a 180, which is allowed. So after 180-degree rotation, now the 4, it will be definitely either above or below the plane. Then leave it and rotate, and then we can check whether it is R or S. Now, how we check the optical isomerism? So to check the optical isomerism, we take a polarimeter. We know that the ordinary light, it has vibration in all direction, but when we pass through the Nicol prism, its vibration become in one direction. So it is there like this. And when we pass this light through a polarimeter, in which there is a tube and where the solution is kept. So it rotates the plane polarized light in any direction. If we rotate the plane polarized light in right direction, then this compound will be called dextrorotatory. And if in left direction, this compound will be called levorotatory. And if it is not able to rotate the plane polarized light, this compound will be called meso or racemic. Now, what is the difference in meso and racemic? Meso means there is the internal compensation, or we can say there is any type plane of symmetry which make the compound optically inactive. Racemic means there is an external compensation, that is, we mix the compound in 50% D and 50% L. And that's why they cancel the rotation. So this compound will be called racemic mixture. So both are optically inactive, both can't rotate the plane polarized light, but meso is there is a defect in internal structure, and in racemic, here we mix the externally. Now, dextro and levo. So in dextro and levo, we generally this two term we generally understand with the term enantiomer and diastereomer, which I explain in next slide. So now the specific rotation. The rotation is generally defined in terms of a specific rotation, which is a physical constant for the amount that a chiral compound rotate plane polarized light. It is shown by alpha, and which is generally we can say alpha or theta, and which is equal to observed rotation divided by length of sample, which is kept in polarimeter tube in decimeter, and C is the concentration in gram per ml. Generally, length is given in centimeter, so we can easily convert by taking 1 decimeter is equal to 10 centimeter. So here we took T and D. T means temperature, which is of 25 degrees centigrade, and D is the wavelength, which is 589 nanometer. Now the next term is enantiomer and diastereomer. So enantiomer means the pair of molecule which are mirror images of each other, but they show non-superimposable mirror image. It means if we take dextro, and definitely its mirror image will be levo, or if we take R, then definitely its mirror image will be S. So if we take a pair of dextro and levo which are optically active means non-superimposable mirror image, while the diastereomers, these are the non-superimposable non-mirror image. That is, we take another pair with dextro or levo which are not same and non-superimposable. Now, Next is enantiomers they show same physical, same chemical property, but the optical rotation is different. It means if one in pair, if one molecule show optical isomerism plus 20, optical rotation plus 20, then definitely the second pair, second compound, it will show optical rotation minus 20 degree. So simple, they show same, similar, identical physical and chemical property except direction of rotation about plane polarized light. While in diastereomers, their physical property may be similar, but the chemical properties will be definitely different. In enantiomers, generally, they are present in pairs, which are mirror images, while in diastereomers, they can be several molecules. Now, if we take an example of tartric acid, suppose. So, in tartric acid, the molecular formula is, structure is COOH, COOH, H, OH, OH, and here is H, here is H. So, if we write the tartric acid like this, so it is clear if we imagine a plane. So, it's cut the compound in two equal half. So, it means it is optically inactive. So, this form, it will be called meso or DL. Now, if we write the structure like this, COOH, COOH, one is H, one is OH and H. So, in this case, if it is D, so definitely its mirror image OH, H, H, OH and COOH. It will be L. This is not, sorry, OH, H, OH and H. And in a simple, we can say rotation. So it is clockwise, so it is D, and it is anti-clockwise, then it is L. So in this case, this pair, it is an enantiomer. But if we make a pair of this with this and this compound with this, these are called diastereomers. Is that clear? So enantiomers show optical activity, but they are mirror images of each other. Now, the last term is optical enantiomeric axis or optical purity. Now, enantiomeric axis is the measurement of the axis of one enantiomer over the racemic mixture. For example, if we see or if we say that the racemic mixture is 25% in enantiomeric axis, that is the one form, it is axis in 25%. So, remaining 75, and in 75, half will be D and half will be L. So, enantiomeric axis is equal to percentage of one enantiomer minus percentage of another enantiomer. For example, if mixture contains 75% of one enantiomer and 75% of other. So, that is if we find the axis, so it is of 50% axis. So, one enantiomer will be 55% axis in an enantiomer racemic mixture. It is numerically equal to optical purity, and which is equal to optical rotation of mixture divided by optical rotation of pure enantiomer multiplied by 100. The second, we can find this enantiomer axis by D minus L upon D plus L into 100. So, suppose this is a question. So, 3 gram of plus 2 bromobutane and 2 gram of minus 2 bromobutane. And the specific rotation is given, which is 23 degree. Find the specific rotation of racemic mixture and enantiomeric axis. So, we can apply by these two formula, D minus L upon D plus L. So, we get the enantiomeric axis, which is 20, and specific rotation 4.6. So, if compound is suppose 50% in axis. So, 50% in axis means 50% will be one form, and the remaining 50, 25 plus 25, that is The A, it will be 75% and B only 25%. So, I'm ending this lecture, and in next lecture, I'll discuss the compound which show optical isomerism without chirality and geometrical isomerism. Thank you.